Actually, one of the few pleasant things of the department chair is that I get to give awards, particularly teaching awards, to graduate students. So today is the time to actually award the Paul Kirkpatrick Award for undergraduate teaching. This award was established to recognize those graduate students who have demonstrated talent and commitment to teaching of physics to undergraduates, therefore exemplifying the dual commitment to teaching and research characteristic of Kirkpatrick's own scientific life. He was a distinguished member of the Stanford Physics Department for 28 years, before retiring in 1960. And then he died in 1992 at the age of 98, which is, I think all the awardees have a track, have a path to that sort of advancing. Although well known for his 40 years of work in X-ray research, and in particular the invention of the X-ray microscope, and for his pioneering work on holography, long before the invention of the laser, obviously he retired in 1960. He is at least as famous for the spirited championship of the importance of furthering excellence in teaching in physics. His traits of character, integrity, and compassion were much admired by his colleagues, family, and friends. Many of our Kirkpatrick awardees have gone on to distinguished careers in teaching, in teaching physics. We're grateful to the original donors for establishing the endowment that funds those awards. So those two awards, the first one is given to Olivia Ghosh. Yeah. And the second one is Ryan Linehan. Where's Ryan? I thought Ryan was supposed to. Oh, there he is. Sorry. Very much. And okay, congratulations. And I guess you got the important thing, that's the check separately. All right, with this so it's a pleasure to introduce another Kirkpatrick Award winner, Ken, who was born in Belgium. Then he went to MIT, where he published a couple of fairly well-known papers. I was just looking that have over 1,200 citations so far. So that record, undergraduate record, earned him admission to Stanford. And so he had one of the most colorful and interesting files as a member of the undergraduate admission committee. So he was admitted with flying colors, and he joined SIPP about 10 years ago. After he graduated, he went to the Institute of Advanced Studies and NYU, a joint postdoctoral position. And after a year in Santa Barbara, he became a professor of physics at NYU, where he is now for the last couple of years. So he has worked on a broad range of things, from collider physics to then physics beyond the standard model, astroparticle connection, and also small-scale experiments for looking for physics beyond the standard model. And today he'll talk about such a topic. Thank you.
Thank you, Salas, for the very nice introduction. It's great to be back here and seeing many familiar faces. I've asked many of you embarrassing questions in classes, so feel free to ask me embarrassing questions today, as well as insightful ones. So yeah, it's great to be back in a room where I proctored exams and gave review sessions too. Okay, everyone on Zoom can hear me okay? And one the Kirkpatrick, sure. So hopefully I'll do an okay job teaching you about this topic here today. So Stanford is one of the birthplaces of small scale experiments, very weird detectors that look for original types of physics or new types of phenomena like dark matter. So today I will also tell you about such an unusual detector that looks for an unusual dark matter phenomenon. And it's also odd in a different sense. Let's see if I can change my slide. Okay, so what I will tell you about today can be divided into 4 parts. So first I will tell you a little bit about discrete spacetime symmetries under which these phenomena are odd in a precise sense. And I will also tell you about a puzzle in the standard model related to these symmetries. Second, I will tell you about a solution to this puzzle, and that is the quantum chromodynamics axion, which is a dynamical solution to this puzzle. And then for the third part, I will tell you about a new phenomenon that we discovered, at least on a piece of paper, that can be caused by this QCD axion. And then I will sketch out on this piezoaxionic effect, as we call it. Okay, but first about physics can be organized by its symmetries. So, and by symmetry, I mean an operation under which the laws of physics are invariant. So most famously, we have space-time symmetries that are continuous. So for example, physics should be invariant on a moving train versus a coordinate system here on the ground. Likewise, physics is invariant if we rotate our coordinate system or if we do translations. There's also a number of discrete symmetries, space-time or internal. So where we exchange particles and antiparticles, which is charge conjugation. So antiparticles behave very similarly to regular particles. Likewise, under parity, many laws of physics are invariant. So the mirror world looks more or less the same or exactly the same. And under time reversal too, so physics is invariant if you play it backwards. So gravity and electrodynamics are such examples. And finally, there can be also more sophisticated symmetries, which I call internal symmetries, related to how fields transform, and symmetries related to the conservation of certain charges in the standard model. So some of them are exact, or we think they are exact, such as the continuous space-time symmetries that I wrote down here. Also, we think that any quantum field theory preserves the combined action of these 3 discrete symmetries. And finally, we think that the gauge symmetries of the standard model are also exact. The baryon minus lepton number, we don't know. I won't say too much more about that. And we know flavor symmetry is broken. So, not all quarks are the same. They have different masses, etc. But it was found out in the second half of the 20th century that physics in a mirror is not exactly the same as in our world. So we can know that we're in this world and not the mirror world. So the laws of physics are not invariant under reflections in space. And a bit later, it also became clear that the laws of physics are not exactly invariant under reversing time. And because the action under these 3 symmetries together is a good symmetry, that also means that particles don't exactly behave like antiparticles. Okay, so the only reason for why we're not so familiar with, let's say, the breaking of parity and time reversal symmetries is that most physics at low energies, like gravity and quantum electrodynamics, does preserve them. But it's pretty clear that in the standard model, these symmetries are broken badly. For example, left-handed particles have different charges than right-handed particles. Likewise, there's no sense in which the time reversal violation is small, except for the fact that some particles are heavy and there's approximate flavor symmetry. So we know, we think we understand sort of the symmetry breaking pattern of particle physics. Except there's one thing we don't understand, which is why parity and time reversal is so weakly broken in the strong interactions. So let's talk about this a little bit. So this is what I mean by parity transformations, in case you forgot. So let's imagine we have a clock in our world, right? It goes clockwise by definition of the word clockwise. You can distinguish a clock in our world from one in the mirror world, where here I've taken x to minus x, for example. So this has a different orientation. If you found a clock like that, you would know that it was made in the mirror world and not in our world. But so in this mirror world, the minute hand still goes from 12 to 3, like it does in our world. It would just have a weird notation or a weird font. So if you now take our clock and do a time reversal operation, then you could still read the numbers pretty easily, but the minute hand would go from 3 to 12 instead of the usual direction. And finally, it could be doubly weird of going from 3 to 12 and have a weird font in the mirrored world that's also running in reverse. So you could tell based on the clocks you find which world you find yourself in. And it appears like a clock itself breaks both parity and time reversal symmetries. Yes.
Sorry, just checking the Zoom. Your slides are not appearing perfectly. They're being clipped off, and some people were commenting on it. Maybe you want to stop share and start share again.
Okay, sure. Maybe my whole desktop.
That looks better.
Okay. Thanks. Okay, so I just told you about macroscopic clocks. Let's do a microscopic example, that of the neutron. So the neutron you can kind of think as a spinning clock in some sense as well. So the neutron has a magnetic dipole moment, so aligned with its spin, so which I'll call mu, and be labeled by this red vector. And the neutron is a composite particle that's overall neutral, hence its name, but it's made out of charged particles itself. So 3 quarks, 2 positively charged ones, and 1 negatively charged one. So if parity is broken, there's no symmetry reason for why it can not have a dipole moment either. And let's see that in detail. So let's say neutron has a magnetic moment, as we know, and let's say it had an electric dipole moment vector 2. In the mirror world, if we take 3D space and send all the coordinates to negative themselves, then the magnetic dipole moment, which is a pseudo vector, should not flip, but the electric dipole vector, which is a regular vector, should flip. So if you found a neutron here, just like this parity flipped clock, you could figure out you would figure out that you lived in the mirror world and not in our world. So the presence of a simultaneous presence of a magnetic dipole moment and an electric dipole moment of a neutron would violate both parity. Would violate parity. Likewise, the simultaneous presence of these two vectors would also violate time reversal. So if you run it in reverse, you can think of a magnetic dipole moment as a current that goes around. Let's say if these charged particles had some angular momentum, it would be like a current going around inside the neutron. You could think of it that way. And so if you run time backwards, the current would reverse and the magnetic dipole vector would point down. So this arrangement is also, you would find that in this time reversed world, the neutron would look different. And if you do both, it wouldn't. At least not at this level. Okay. So it seems like a clock and both a neutron with an electric dipole moment would break parity, for example. Let's do an example in QED where we describe, let's say, the hydrogen atom. So here we have just a positively charged proton and electron. The electron can have a magnetic dipole moment. Let's say we polarize it upwards. So magnetic dipole moment points up. This arrangement of charges where the electron is to the right of the proton would have an electric dipole moment that points left. but if we, so this would also have some simultaneous presence of a magnetic moment and an electric dipole moment. But if we compute the ground state of a hydrogen atom, the electron is not always to the right of the proton. In fact, it's in a spherically symmetric state around it. And if you compute what the electric dipole moment is with the standard formula, you would find 0, at least an expectation value. And then in the parity reversed version would not look any different than the normal version. And likewise, in the time reversed version of the hydrogen atom it would flip the spin, but such a state also exists in our world. So you wouldn't necessarily be able to tell the difference if you lived in our world or the time reversed world. And likewise, if you do it both. But I told you this puzzle about, clocks violating parity, but that's actually not quite the same. So let me give you another macroscopic example. So Rafael Nadal is famously a left-handed tennis player. So why does Rafael Nadal not violate parity? Why is the presence of a left-handed Nadal not an indication of parity violation? Well, and the point is macroscopic systems, including Nadal, are quantitatively very different. And the reason is they're polarized due to the environment. So you can, unlike a hydrogen atom, he's not an isolated system. So in particular, if we work in the body fixed frame, this vector A points forward because he wants to face the tennis court if he's to win matches. Likewise, his head points upwards if he has to stand on the ground in any reasonable way. And he also found it energetically favorable to be a left-handed tennis player because there's a lot of right-handed tennis players. And so he's very easily polarized because quantum mechanically, you can actually compute how much energy it takes to polarize, let's say, these three vectors. And quantum mechanically, this is just h bar over his moment of inertia. Moment of inertia is just the mass times the typical size squared. Let's say 50 kilograms times a meter to an order of magnitude. And then you get 10 to the minus 52 eV. This is a tiny energy splitting. This would be the energy splitting between Rafael Nadal's S and P-like orbitals. And the tiniest change in the mass of the sun or some asteroid in a neighboring stellar system would be enough to polarize him. And certainly these three environmental effects. So if you could really shield him completely from all of those effects, he would be like a hydrogen atom and he would not have any preferred direction. Okay, same with the clock. So the point is small systems can be effectively shielded enough and they have large enough energy splittings that we can search for parity violation. So sufficiently shielded systems like this hydrogen atom shouldn't have any simultaneous magnetic and electric dipole moments. So the weird thing is that in fact, the symmetries of the standard model allow for parity violation and time reversal violation. So they have an interaction term, it's called the theta term, that is both P odd and T odd. So this term is like the electric field dotted into the B field. The B field is odd under time reversal and E is not, and E is odd under parity and B is not. So this parameter is odd, so flip sign under parity, and it's separately flip sign under time reversal. And there's some technicalities here. The actual physical angle is a combination of this phase and the phase in the quark mass matrix. So the sum is the physical angle. And we know that the phases in the quark mass matrix are not particularly small. So we expect this theta angle to be some order one number between 0 and 2 pi. Okay, so, well, it's a parameter. Now we can make physical predictions in the standard model. And so you go and try to predict things theoretically. And your prediction is that the neutron's electric dipole moment, this vector here, is this angle theta, which is a dimensionless number, times 10 to the minus 16 e centimeters. So it's basically one electric charge times the size of the neutron times theta, and then times maybe divided by a factor of 1,000 or so. But we don't expect this electric dipole moment in natural units to be that much different from this magnetic dipole moment vector. Except apparently, we tried to measure this and we found something that's 10 orders of magnitude below the naive expectation. So this begs the question, why is the violation of parity and time reversal symmetries so small in the strong nuclear interactions? Why is this composite object made out of charged, strongly interacting particles not parity and T odd, when clearly there's no symmetry forbidding it, unlike in QED? Okay, so that's the central question. Why is parity and time reversal symmetry so well preserved by the strong nuclear interactions? So that's called the strong CP problem. So it's doubly weird because physics doesn't, other than this dipole moment, doesn't really change very much as we change this theta. So this theta angle can go from minus pi to plus pi, but this electric dipole moment is very small. It doesn't affect the structure of matter in any way. And it's strange because so it basically means there's no anthropic explanation for the small theta angle. If theta was 10 to the minus 2 or 10 to the minus 3, physics would be exactly the same. You could argue that it's maybe not pi because then the pion mass and the structure of nuclei would be vastly different, and the shapes of nuclei. But you couldn't really argue anthropically for extremely small theta angle. And this is unlike the case for the Higgs mass and the cosmological constant. These are also two weirdly small numbers in the standard model, but physics would look vastly different if the cosmological constant were bigger. For example, the universe would be a lot sparser if the cosmological constant were bigger, and if there's a few orders of magnitude larger, galaxies wouldn't even come about in the first place. And likewise, if you change the Higgs mass by a factor of 2, there's a linear dependence on, let's say, the size of an atom on changing the Higgs mass. But not so for theta. So it begs the question, why are we really sitting here? And you know, one answer to this question lies in this graph, perhaps. So if you compute the energy density of the universe, at least the contribution from the strong interactions to the cosmological constant, you find that this is minimized here at 0. So theta is a parameter. If you set it here, it would just stay there. But then it was noticed, although not exactly by this logical reasoning, is that if you make theta the dynamical degree of freedom, if you say that it's now a field which can fluctuate, well, it would be like a skater in a half pipe, and it would want to roll down like a ball on a ramp. So it would oscillate a little bit and eventually settle down in the minimum because the potential is minimized there. And so if you had such a situation, this would dynamically explain the smallness of this effective theta angle over time. So this is what we call the QCD axion. It's a one parameter model specified by this decay constant FA here. The only thing, the FA controls the properties of the QCD axion. In particular, this curve is always the same. It's just set by the strong interactions. But as I increase FA, the effective curvature in A itself is larger. So that is smaller. And if I decrease FA, the mass would be larger. So there's a relation between the mass and the decay constant that's like so. So for a very large decay constant, this particle would have a very low mass, lighter than all of the particles in the standard model, except for the massless ones, of course. And also, this particle, again, is described by one parameter. So this one parameter controls both the mass and the coupling to gluons. This parity-violating coupling to gluons. So again, this is a dynamical solution to this strong CP problem. And besides this gluon coupling, there's also some more model-dependent couplings to photons and fermions. But there's a second thing that it explains. So the dynamics associated with this solution carry some energy density in it as well. And it turns out that for this value of the decay constant parameter, that if you set the initial angle in the universe of this field to order 1, the resulting energy density in this field today would correspond to the dark matter energy density. So this particle could explain both the strong, would solve the strong CP problem, this apparent weakness of the parity violating interactions in the strong interactions, but it would also potentially explain the dark matter in our universe. And so you can think of this particle today as some coherent wave, kind of like a radio wave, where the frequency is set by the mass, and it's a coherent wave with a very long wavelength because the mass is small and the particle is moving very slowly because it has to be dark matter. Okay, so we've looked for this particle in many different ways. So in particular, it can couple to photons, just like it can couple to gluons. I'm not going to go through all of these experiments, but the typical prediction is that the particle lives somewhere on this line, whereas I decrease Fa or I increase coupling, I go here, and as I increase Fa, I decrease the coupling and I move further down to the left. In particular, this axion is so light because if it was heavy, it would be more strongly coupled and it would be able to be produced in horizontal branch stars or the sun. We haven't seen any significant changes in these astrophysical objects, so therefore the axion cannot be strongly coupled there. But it can live anywhere along this line. There have been there have been cavity experiments looking for this axion through this coupling that have been very successful and have been running for many years. I'm not going to go through them in detail, but there's lots of follow-ups, so lots of projections for future sensitivities being developed. In particular, also here at Stanford with Peter Graham and Kent Irwin that look for effects of QCD axion dark matter. Okay. So yeah, these are some of the experiments. It's a big cavity in radio frequencies that looks for this axion conversion into a mode of this cavity in a B field. And there's a low frequency version of the experiment being developed here. This particle can also couple to nuclei, so neutrons in particular, where again, if it's, so this is the coupling to neutrons, and this is the mass. If it's in the QCD axion is again on this near this 1 parameter line. If it's very heavy, and strongly coupled, it would again be produced in these hot nuclear systems like the proto-neutron star of a supernova, or in the cores of neutron stars, and would cool the star in excess of what is allowed by observation. So it cannot be too strongly coupled or too heavy. Indeed, there's also experiments that are projected to be able to be sensitive to parts of this parameter space, including some non-QCD axion-like particles. And there's some constraints as well from laboratory experiments. The coupling that I'll be talking about today is this irreducible coupling to gluons. So really here, there is a tight prediction for what this coupling is as a function of mass. So the relevant parameter space we're going after is this yellow line here. And again, in an experiment proposed by Peter and Surjit Rajendra and Dima Budkar, when they were in the area, they proposed the first experiment that is of which prototypes have already been built that is looking for this irreducible prediction of this QCD axion dark matter. And in future phases, we'll hopefully be sensitive to this parts of this parameter space. So the thing I will be telling you about today also lives in this space. And again, we want to look for masses in this regime that are still, for the most part, allowed by current constraints. And notice that this corresponds to looking for waves between, so I said the dark matter wave you can think of as some oscillating wave at a particular frequency. So, sorry. This mass range that I'll be talking about corresponds to tens of kilohertz or a few kilohertz all the way to terahertz. So that's sort of the range of frequencies. And the two experiments that I'll be talking about today cover the low frequency band from tens of kilohertz to about 100 megahertz. And then there's also a non-dark matter, non-QCD axion dark matter experiment that we're currently working on. But I will mostly talk about this blue region here. Okay, so I've told you how, why it's so weird that parity and time reversal is so weakly broken by the strong nuclear interactions. I've also sketched out this dynamical solution that we call the QCD axion that can solve that problem and furthermore can be the dark matter of our universe. And as a bonus, it is testable through a variety of phenomena. But in this talk, I will talk about a new phenomenon that we found out recently that we call the piezoaxionic effect. But before I tell you about the piezoaxionic effect, I want to tell you about another effect with a similar name called the piezoelectric effect. So let's review first what happens for a non-piezoelectric material, let's say just table salt, where these could be sodium and chlorine atoms. So if this is the ground state of the material and you compress it, let's say, nothing much happens. So no electric field is developed in this material because this material has a center of inversion, right? So if I put the origin of my coordinate system on this atom here, and I flip it around, so if I take x to minus x, it would look like the same crystal. So the invariance of the crystal under this symmetry forbids a vector being developed under compression, because if it points this way, if I did a parity transformation, it would point that way, but the material hasn't changed. So symmetry in this particular material forbids an electric field developing at linear order under compression. But there are materials that are kind of like the Rafael Nadals of crystals that break parity spontaneously. So quartz is one example. And this is kind of a toy picture of what quartz looks like. But this particular crystal breaks parity. So if you have a hexagonal lattice here, quartz is not exactly hexagonal, but this is a useful illustration. This particular crystal has no center of inversion. So there's no point in this crystal where I can take x to minus x and get the same crystal back. And as a result, if I, for example, take this crystal and I stretch it horizontally, then because the stretching of some of the directions is more easily performed than other directions, I get a charge difference across the crystal. So yeah, so these two negative charges move a little bit more than that charge, and you get a charge difference across the edges. And likewise, if I compress the crystal, this positive charge moves further out than do any of the other charges, and I get a positive charge on the bottom and a negative charge on the top, because that one, this charge moves quite a bit as well. So I get a linear relation between a CP even quantity, which is stress, which could be tension or compression, and a CP odd quantity, or sorry, I misspoke. A parity even quantity, like tension and compression, just stress, and a parity odd quantity, which is an electric field, that flip sign, if I do a parity transformation. So yeah, and this is possible because the crystal itself violates parity. And so quartz is not exactly an hexagonal lattice, but if you look in detail at the structure of quartz, you find that the chains of silicon and oxygen are arranged in a helix, and the helix can be left-handed or right-handed, which determines the sign of these effects. And based on these symmetry arguments, the brothers Curie, so Pierre and Jacques Curie, in 1880, theoretically predicted that such a phenomenon should occur. So they took a bunch of materials, quartz, tourmaline, Rochelle salt, cane sugar, and they tried to prove that this worked, and indeed they were successful. So in 1880, they discovered the direct piezoelectric effect. Literally, they squeezed some things and they got electric fields out. And then a year later, in 1881, Lippmann said, well, based on thermodynamic arguments, there's also a reverse process that should happen, which is the converse piezoelectric effect. So if you apply an electric field to a material like this, you should squeeze it itself as well. So you can cause a stress in materials by applying a field. And then the Curie brothers later tried to measure this and directly found this as well, almost in the same year. And I mean, today, there's lots of applications built on piezoelectric crystals. Sonar was developed based on this technology and this phenomenon. I think your watches and your iPhones have little piezoelectric resonators in it as well. So the way we describe it is with these constitutive equations. I'm not going to write all the indices. So the way it works is a stress is caused if I strain a material with a proportionality constant, that's the stiffness tensor. But in a piezoelectric material, I can cause a stress as well with some electric displacement, D. And the proportionality constant is the piezoelectric tensor H. And likewise, I can cause an electric field if I strain the crystal or if I have some electric displacement. And so just investigating the symmetry structure here you can see that you can get a parity odd quantity from a parity even quantity, which is a strain. So that's only possible if an intrinsic property of the material is parity odd. And in the case of quartz, it is. So I'm skipping ahead a little bit here, but what we are going to show is that there's an analogous effect, which we call the piezoaxionic effect, where an axion background, parameterized by this theta, can cause a stress in a material. And so investigating, and so we call this new tensor here, the piezoaxionic tensor, and this tensor there, the electroaxionic tensor. And so let's investigate the symmetry structure of that new term. So for example, so we saw before that this axion is parity odd and odd under time reversal both. So if we have polarized nuclear spins in our material, they form the source of time reversal breaking. And then if the material itself is also parity odd, like a piezoelectric crystal is, for example, then there's no reason why I can generate, let's say, a stress in a material in a background of axions in a material with polarized spins. And I'll go through exactly how we compute this and what the effect is. So the basic idea is that so in a crystal without a center of inversion that contains polarized nuclear spins, this dark matter Q-city axion wave that's both parity odd and T odd can excite mechanical stress. And from what I've told you before, is just based on symmetry arguments, right? So there's no symmetry reasons for why I cannot cause a mechanical stress in such a material. And likewise, the converse effect. If I have a crystal without a center of inversion with polarized nuclear spins, there's no symmetry reasons for why that cannot source Q-city axions, just like an electric charge cannot source. There's no symmetry reason for why an electric charge cannot source an electric field. So I've just given you the symmetry analysis, and hopefully I convinced you that this effect is not zero, but I haven't told you how big it is, and it's not very big. And I will not take you to the details of the calculations, but just sketch it out. So I've told you about the Q-city axion. And first we'll see what effects that has on the nuclear properties. Then I'll show you what effects it has on atomic properties. Then we calculated what the change in atomic properties of this Q-city axion will have on a crystal, a piezoelectric crystal in particular. And then I'll sketch out what the readout is at the end. So first the nucleus. Before I do that, I have to tell you about Schiff's theorem. So Schiff's theorem tells you that it's kind of unfortunate. It tells you that if you have a system that has primarily electrostatic interactions, like a hydrogen atom, or in reality just a crystal of charged point particles, right? Which any of these things are. Any electric dipole moment of any of the particles are perfectly screened by just rearranging the positions of these particles. So if a nucleus had an electric dipole moment inside a crystal that is unobservable if the particles are point particles, and if you only count electrostatic interactions. So that's why, but nuclei are not point particles, they're composite. So it turns out that the leading effect will be caused by the Schiff moment, which you can think of as an electric dipole moment weighted by the radius squared inside the nucleus. And thankfully for us, there are some Rafael Nadal analogs among nuclei also. So certain nuclei, radium and radon, for example, in their body fixed frame, they violate parity. So they have a pair shape that is in their body fixed frame. If you do a parity transformation, is not invariant. Now, if there's no Q-city axion, this pair shape wouldn't have any preferred direction. So the pair wouldn't point in any particular direction, just like the electron in a hydrogen atom doesn't point in any particular direction away from the nucleus. But what you can show is that the interactions among nuclei are slightly changed by the presence of this axion background, and can lead to an alignment of this pair shape, which is the radius squared weighted electric dipole moment, and the nuclear spin. So the nuclear spin is T odd, so time reversal odd, and the nuclear shift moment is parity odd, but time reversal even. So a proportionality between these two properties. So the alignment of this pair shape axis with a nuclear spin violates both parity and time reversal symmetries. And the Q-city axion can do that. So this was well known, but the basic effect is that this pair shape would align ever so slightly with the nuclear spin, in an oscillatory way as this wave oscillates. And the size, you can calculate the size of this effect, and it's about the effective size of, the effective volume of the nucleus times an electric charge times this theta angle, which is extremely tiny, about 10 to the minus 19. So that's what I said before. So these axion couplings can align this pair shape with the nuclear spin. So that's one element of the calculation of how the QCD axion affects nuclear properties. So how does that affect an atom? So here I've drawn this pear-shaped nucleus that's slightly aligned with the spin, which is the red vector. And of course, in a crystal, and therefore in an atom, there's some electron cloud around this nucleus. And so what it is doing is it's the pair shape is oscillating as the axion dark matter wave is oscillating. And the way it back reacts on the electrons is through an operator like that. There's an energy shift associated with flipping this shift moment. And you can think of it as a dot product of the shift moment with the gradient of the electron density at the nucleus. So it's a very short range interaction. This you can compute reliably, and you only really need to know about the energy levels of the S and P orbitals because those are the ones that have significant overlap at the nucleus. Finally, we can estimate how this back reacts on the crystal. So broadly speaking, you know that the Hamiltonian of the electrons is sourced primarily by just the crystal potential. So all the arrangements of charges and this new perturbation, which is from the shift moment. And so in a piezoelectric crystal, this crystal potential mixes S and P electrons with some wave function coefficients specified by these epsilons. So in such a crystal system, so we first solve this Hamiltonian, find the full electronic wave function. You can do some approximate methods with density functional theory to do this. You then compute the energy shift of this shift moment. And this shift moment Hamiltonian is parity odd. But if you compute this then between opposite parity states, so between S and P orbitals, you find a tiny energy shift, about 10 to the minus 24 electron volts, so 10 to the minus 25 Rydbergs or so, if the shift moment is of the size you would expect from a QCD axion. And then this piezoaxionic tensor, this Xi tensor is just how much this energy shift changes under strain. But in a piezoelectric crystal, this is predicted to be non-zero. And we can compute this, at least in principle, with density functional theory for any crystal we want. So that's the piezoaxionic effect. Basically, our claim is that axion excitations, so an axion dark matter wave, can cause electromechanical excitations in very particular materials. So parity-violating materials like quartz, which also have polarized spins in it, and vice versa. So these types of materials can also be the source of axions. So in the last 10 minutes or so, or 7 minutes, I will sketch out 2 detectors based on these 2 piezoaxionic effects. So the converse one and the direct one. So the idea is to take a crystal that's piezoelectric, so it doesn't have a center of inversion, polarize the nuclear spins. And if you do that, the converse piezoaxionic effect says that if you have this dark matter wave and this type of crystal, there would be a mechanical stress excited in this material. And if you align the crystal tensors and if you cut the crystal along the right direction, it would cause a resonant acoustic excitation. So just like a tuning fork, you would excite an acoustic wave, the normal mode of this crystal. So you would change the thickness of this piezoelectric plate resonantly. And so this mechanical excitation, because of the piezoelectric effect, would cause a voltage difference across these two electrodes as well. So again, if you strain this piezoelectric crystal, there would be a voltage difference across the plates, or charge accumulation on these two electrodes, which are capacitor. And so you have some electrical signal that you can then read out with a sensitive circuit and a squid detector system. So I'm not going to go through all of the details, but you can do some circuit analysis of how exactly this system interacts with your detector. And I'm just going to sketch out some basic things. So in particular, you can think of this piezoaxionic effect as a voltage in your system, which is extremely tiny. So here I'm plotting this axion voltage as a function of frequency around one of these mechanical modes, around the first thickness mode of this crystal. So the first thickness mode of this crystal is at 60, 62 kilohertz, if it's 4 centimeters across. And the typical size of the voltage is 10 to the minus 15 electron volts or so, and a bit higher on resonance, or quite a bit higher on resonance. So those are the types of voltages that one is looking for. The main noise sources in this experiment are just the thermal noise, the Brownian noise in the crystal itself, which is this blue line. So as a function of frequency, this is on the order of a few times 10 to the minus 14 volts per unit bandwidth in hertz. There's some thermal noise in this inductor that's used for the readout, and then there's some finite readout noise, which is from how well you can read out any resulting flux in your squid device in the end. So that's by far the limiting factor off resonance, but on resonance, you have quite good sensitivity, and you can resolve these thermal noise sources of your detector. And so basically you only have sensitivity in this peak where you're where the flux noise from the squid is not quite so bad, because you're reading it out resonantly. And thankfully we found a clever way to scan this resonance. If you have a crystal, you cannot change the normal mode frequencies very well, but by coupling, because the crystal is piezoelectric, it knows about the other circuit elements as well. It's like if you take a harmonic oscillator and you change the effective load, like you add a little bit of mass, so you change the resonant frequency of the experiment. And indeed, if you just take the crystal and you ask how, as a circuit element, where is the resonance? So here I'm plotting the impedance of the circuit as a function of frequency. It has this resonance, which is this black line, which is this black dip here. So that's where your experiment would be sensitive, in this tiny bandwidth around this frequency. If let's say you forget about all of the other stuff. But then if you add some inductance, so if you just complete the circuit and you add a regular inductor to it, you change the frequency of this resonance. So this acts like a load, and you can change the position of this resonance and effectively scan. And likewise, if you increase it a bit more, you can shift this resonance all the way to the left. And if you increase it enough, there's some higher harmonics that you see as well. So this crystal has a bunch of acoustic modes, and you can tune them around by changing the readout circuit. And so if you for one particular state of the inductor, this would be your sensitivity to this theta angle. So it's very good on resonance. And the QCD axion prediction is by this green line. We don't know what frequency it occurs at, so we have to scan over all the masses we can. And hopefully one gets to this line. So this is for like a projected sensitivity with an optimistic setup of a 4 centimeter crystal. And this red line would represent a few hours of integration time. If you do this many times at many different locations and you step through from where this peak location goes from here to there, and if you combine optimally all of those observations, you get an effective sensitivity that looks like this, with a small blind spot in the middle that I can talk about later if you like. So this is for one particular crystal and a 1 year integration time. You have some small fractional bandwidth of order 10% that you can perhaps get sensitivity to the QC axion too. Okay, if you have, this is one of my final slides. If you then take a bunch of these setups, so if you take 13 different crystals, any one of them has a 10% bandwidth, order 10% bandwidth. But if you take 13 of them with slightly different thicknesses, so one of 4 centimeters, maybe one of 3.6, 3.2, etc. So if you have some logarithmically spaced crystal thicknesses between 4 and 2 centimeters, 13 of them, and you integrate for 10 years, you would be able to cover one octave, so a factor of 2 in frequencies to this QCD axion, a dark matter parameter space. Yeah, and so if you take a different geometry or just a smaller overall size of the experiments, where the thickness of your crystal is 4 to 2 millimeters, and you multiplex them, so your signal goes down as the resonator gets smaller. But if you can multiplex them in series or in parallel, you can retain sensitivity at these smaller dimensions as well. And ultimately, if you can do mechanical loading and avoid this peaky structure, we think maybe you can get 3 to 4 orders of magnitude in frequency space in an experiment like this. So I think I ran mostly over time, but I just want to show you one thing that can be done in the near future. So I've mostly told you about the irreducible coupling to the QCD axion, but the axion-like particles can also couple to electrons. And the non-relativistic Hamiltonian would be like some effective magnetic field sourced by the axion, as well as a second term that's, as far as I'm aware, not been looked for. And there's experiments of which prototypes have already been built of these sensitive quartz resonators. So it looks like a tiny quartz plate that's 13 millimeters in diameter and a millimeter in thickness that would be sensitive to this coupling already, or something like it could already be run without new experimental development. And so if you literally just take this tiny crystal that's about the same dimensions as a contact lens, and you did an experiment of a day, you would get sensitivity to the QCD axion, or to an axion-like particle here. And with more aggressive setups with centimeter-sized detectors, you would explore new parameter space. Yeah, and I don't think I have time to talk about this, but in work in progress, we're also thinking about how to source axions in the lab, even if they're not dark matter, where we think we can cover higher axion masses by the forces they mediate. And so we're thinking of modifying the source mass of a particular experiment that's already been funded and under construction. Instead of just a regular tungsten source mass, we want to replace it with a piezoelectric material with polarized nuclear spins that can then mediate axion forces that can be detected by it with an NMR setup. Happy to talk about this later, but I think I should conclude now. So just to conclude, let me just remind you of the outline. So I hope I've convinced you that It's weird why parity and time reversal are so well preserved by the strong nuclear interactions. I've showed you a classic solution, probably the one that we most believe in, that solves this problem, and which can be the dark matter as well in our universe. It's testable in a variety of ways, but we think we found a phenomenon that can be the basis of a new type of experiment. In fact, two classes of experiment where mechanical modes are excited by this dark matter wave. So I'll finish here. Thank you.
Question from the audience?
So maybe I missed something, but in your description of piezoaxionic effect, I thought that the nuclei in the crystal need to have a large shift moment.
Yeah.
If I have the terminology correct, they combine like parity, like radium nuclei.
Mm-hmm.
So won't you need to make a crystal that has a sort of strange material out of it, or did I miss that it could just be done with silicon?
Yeah. So it needs to be a particular. It needs to be a heavy nucleus. Radon is not the right one because probably your material would heat and melt if you build it big enough. But yeah, it needs to be a rather heavy nucleus that has this octupole deformation, this pear shape. So this is in fact an active area of investigation. So these pear-shaped nuclei, it's not exactly under good theoretical control, which are octupole deformed. 1 second. Oops, I think I lost the slide. So radium, radon, thorium, they have this octupole deformation. There's a variety of nuclei that are also thought to have this shape, like basically the neutron-rich actinides, most of them that are radioactive and probably not suitable, but some other heavy nuclei, especially in the neutron-poor lanthanides, so barium, dysprosium, europium, samarium, lanthanum. So those nuclei also have this shape and so the size of this shift moment, as you've said, it's proportional to the size of the radius of the nucleus and the electric charge, the total charge of the nucleus. So you want something as heavy as possible, of which you can still grow a crystal. And there's a bunch of piezoelectric crystals with those elements in them.
How do you calibrate this thing? So in other words, can you simulate a signal and show the entire rigmarole really works?
So you can calibrate the frequency response just by knocking it with a hammer. That's how these old Weber bars have been performed. The overall magnitude of the signal is harder to calibrate. So the overall size of the coupling unfortunately has some uncertainties with it. Basically, the main ones is the calculation of the size of the shift moment. I think the crystal calculation, so of all of these steps, I think the atomic perturbation is under very good control. The only thing you need to know is sort of the energy levels of the SNP valence electrons, which you can measure in the lab. The step to go from these atomic perturbations to the crystal potential, you can calculate with 20–30% accuracy with density functional theory. So yeah, the biggest uncertainty is in this calculation here. But we've contacted some nuclear theorists, including Jonathan Engel at North Carolina, that are hopefully going to run some more simulations or some calculations of how big these shift moments are. Yeah, one more thing. So actually, there might be some progress. So if nuclei with these strong pair shapes would have some weirdly enhanced internal decay rates, so octupole transitions between, so would have weirdly fast radioactive decay rates of some of the excited states. So you can do an additional cross check on those calculations as well. Okay. Other questions? Honey?
You have crystals there where you violate time reversal rather than inverse symmetry. And the reason I ask this is, can you have something like a piezo-magnetic material? Because then possibly it might be easier to read how an oscillating magnetic field.
Yeah.
Couple directly to it.
Well, so I should say our material already is not even under time reversal because it has these polarized nuclear spins. We've thought about magnetic interactions. So the nuclear moments that violate parity are electric dipole moment, magnetic quadrupole moment, and this shift moment and electric octupole and so on. So the reason why we didn't use the magnetic quadrupole moment and let's say the piezomagnetic effect that can occur is that if you have a very high concentration of this piezomagnetic effect would only work if you had polarized electron spins as well. So if you had an unpaired electron in your atom, and if you have polarized electron spins, that leads to spin fluctuation and noise that is unbearable. But yeah, so a magnetic quadrupole moment only has an effect on the lattice structure if there's unpaired electrons, and those are problematic for noise reasons. But indeed, you could that signal is there. Yeah, good.
So following up on this question, you mentioned the crystal that people throw as compact lens size crystal. And maybe you said it here, but I missed it. Like that, the way you described it sounded like it was just a quartz crystal. But you have some kind of weird parity nuclear inside, and that's why you're getting sensitivity.
Yeah, so it's the quartz crystal can be used for just this electron coupling. If you want to look for the irreducible QCD axion coupling, you should use a different crystal with this particular nucleus in it. So historically, if you just want to build a sonar with a piezoelectric crystal or a watch in Switzerland, there's no reason to not use quartz or gallium arsenide or simple materials that are easily grown, easily cut, and of which there's a large body of literature. There are many other, so 20 out of 32 crystal classes are piezoelectric. So your chances are good that if you grow a new crystal that it is parity violating. You just have to identify the right one. And the material you eventually want this experiment to be made out of needs to satisfy a list of conditions so that it has to have this nuclear isotope in it that's pear-shaped, has to have good mechanical properties, and be strongly piezoelectric. But we don't see a reason for why such a material cannot exist.
So the projections that you were showing before, like the irreducible coupling,
Mm-hmm.
those projections were based on just assuming some ballpark parameters.
Yeah. So I mean, yes. So a nuclear charge of order 80 and typical piezoelectric tensors for strongly piezoelectric crystals. Yeah.
Okay. For online questions,
I guess.
there are two. One option is if they send the chat.
Yes.
Yeah, Ken just announced that you'll take online questions by chat because they
Okay.
can hear you through the microphone.
They can.
They can hear him.
Okay.
Yeah.
All right. I don't see any at the moment.
Just say it out loud.
Yeah.
Oh, yes. I'll take questions by chat.
Yes.
Good. I don't see any at the moment.
So did you manage to interest any experimentalists to do this?
So the person who's building Ariadne, who's Andrew Garachi, who spent some time here at Stanford.
Mm-hmm.
he is rebuilding. He's rebuilding part of Ariadne. So he's in particular, they're replacing this source mass now. So he is very interested in upgrading the experiment to use a different type of source mass. So the signal is small. So the ultimate reach of their fiducial setup is somewhere along is about this blue line. The one they're building now is the red dashed line. The ultimate prediction, the irreducible prediction for the QCD axion is this purple line, which is about a factor of 10 off of their ultimate reach. But prior to this direct piezoaxionic effect, the naive expectation of the QCD axion signal was here. So they overlooked that if you make the source mass parity violating, there's actually a higher floor to how big this force can be. So it's less pessimistic than it was previously. Yeah. So Andy is very interested.
There are no more questions on or offline. Let's thank Ken again.
Thank you.